Hello, everybody. We're going to continue on section 18H, which is about the definite integral. So essentially, the formal definition is that if we consider the lower rectangle sums and the upper rectangle sums for a function which is positive and increasing between values of x that go between a and b, then we can divide up that interval between a and b into small rectangles of a width b minus a over n. Okay. And we can add up the sums of the lower rectangles and add up the sums of the upper rectangles, and we know that our area will be between those two sums. Okay. So notice that we end up with, this is a formal definition here, but we end up with 1 over n b minus a times f at b minus f at a. Okay. And as we shrink the width, okay, that w part, and we make it very, very small, we're going to have n, the number of rectangles, approach infinity. So as we make the width, the bottom width of those rectangles, those green rectangles, even smaller, we're going to approach having an infinite number of very skinny rectangles. And we're going to find an area for under the curve that falls between a and b. Then that value is going to, that area is going to change and get very, it's going to limit to a specific value is what I'm trying to say. So formally, what we can say is the area under the curve is given by the integral of the function f of x dx between a and b. This is a definite integral because now we have two endpoints to consider our integral on. Okay, so when we evaluate our integral, we now have some boundaries to help us. Okay, and so if we want to find, and from that, we can see that the area under a curve is given by the integral of f of x dx between a and b. Now, Sir Isaac Newton and Gottfried Leibniz showed the link between differential calculus and the definite integral or limit of an area sum. So this math is the same kind of math that Newton and Leibniz were doing. And they stated the fundamental theorem of calculus, which says if I actually want to do this, if I want to find the integral from a to t, in this case of f of x dx, I evaluate the original function at the integral function at t minus the integral function at a, meaning the original function for which this is the derivative. Okay, so if I take the integral of f of x and then evaluate it at t and evaluate it at a, I will get the value for the area under the curve, or the value, theoretically, of the definite integral. And we have a couple of properties of the definite integral that you should know. The integral of a function from a to a is always 0 because this is trying to find the area under a curve where there's no area. If I wanted to find the integral from b to a, that's the same as the negative integral from a to b. So if I'm switching my boundaries around, then the integral is the negative version. If I want to find the integral from a to b and then the integral from b to c of the same function, that's the same as finding the integral from a to c. In other words, I'm finding the area from between a and b under a curve and the area under a curve from b to c. I might as well just find the area under the curve from a to c. And like we've learned before, the integral from a to b of f of x plus g of x, if I'm adding or subtracting two functions, I can split that integral and evaluate each part individually, then add or subtract. If I have a constant in front of my integral, I can pull out, that constant in front of my integral sign. That's this part right here. Okay. Try not to worry about this one. All right, in our next video, we'll take a look at some of these examples. Okay, before we do, I would suggest that you try to watch this video, which I will also link in our weekly planner, because I think it's a good introduction to evaluating definite integrals before we do them together. Thank you.